Well, not every function that we encounter and that has that indeterminate form of 0 over 0 can be factored and broken up in an easy way. For instance, we have seen the limit of g of x as x goes to 0, where g of x is sine of 3x divided by x. If we'd plug in 0 into this function, we would get a fraction which was an indeterminate form of 0 over 0. Previously, we dealt numerically with this limit and graphically with this limit. But how could we deal with this analytically? Obviously, sine of 3x and x are not going to be able to be factored and cancel out like we did with the previous problems. So we need another approach to this. There's lots of approaches that you can use. The one that we're going to look at right now is called the squeeze theorem. So the squeeze theorem says this: if I have three functions which are defined on an open interval containing C, such that g of x is always the middle function for all x that we can plug in there. If the limit of the function f of x is L, and if the limit of the function h of x is L, then the limit of g of x also has to be L. So what that's saying is if the limit of the lower function and the upper function match up with L, then the function in between also has to have limit L. This is called a squeeze theorem because you can think of it in terms of drawing as sort of funneling something in. So that is how the squeeze theorem works. It's basically funneling this g of x into a spot where it's forced to have limit of L. Let me show you how that works just as a very short visual. So look at this example. I have three graphs here. I have a green, a red, and a purple. And you can kind of see that for every value, the green is on top, the purple is in the middle, and the red is on bottom. So for every value of x, we have that. Now, notice how the red and the green converge onto this one point. And if the purple graph is forced to stay between the green and the red, then it too has to converge onto that one point. And this happens in both directions. So the green is on top, the purple is in the middle, and the red is on bottom. And this, if we force the purple graph to stay in between, it gets, quote, squeezed in to the same place where the red and the green are going. So that's what's happening with the squeeze theorem. So let's take a look at that squeeze theorem and let's apply it to sine of 3x over x. Now, notice that I had originally labeled that as g of x. That's so it would align with the middle function here of the squeeze theorem. So we need to find an f of x and an h of x. Now, that on its own sometimes is hard to do, but as far as this example goes, we give a 3 cosine 3x and 3 as our values that will bound sine of 3x over x. So this one has a hint already implied with it. Whereas obviously coming up with these lower function and upper functions, you have to be a little bit clever about in certain instances. So let's take a look at how this would work with the squeeze theorem algebraically. So here we go. Here's our g of x. Here's our limit as x goes to 0. We're finding the limit as x goes to 0 of that. Now, let's take the x values. We have to assign an interval. So let's assign an interval, which includes 0, obviously. So let's assign the interval from negative 0.5 to positive 0.5. I want to look at sine of 3x over x compared to these other two functions. So I'm going to set f of x equal to the 3 cosine of 3x. And I am going to assign h of x to be equal to 3. Now I claim that we get the bounds that we want. So I claim that g is always above f. So take 3 cosine of 3x, and I'm claiming that we always get this inequality. And how could we figure that out? Well, how could we compare this? We can compare this on the interval from negative 0.5 to 0.5. We could look at that graphically and see that's true. We could apply what we know about triangles, and specifically in that interval. So we could apply what we know about triangles and the law of cosines to see that's true. And then we can apply some other techniques as well. For right now, without wasting time, I'm just going to state that that's a fact, and you'll be able to see that graphically if you graph each. The other bound, I'm going to treat the same way. Sine of 3x is less than or equal to 3 times x. You can either utilize some fancy trig stuff, law of sines type stuff, triangle type equalities to see this, or you could graph it. And the way I choose to see that is graph it. Let's take a look at that. We know that this is true on this interval. So if I take the limit as x goes to 0 of 3 cosine 3x, well, based on what we learned earlier, I can just plug in 0 into my cosine function. So we learned earlier that we can just plug things in when my value of x is going to a number in the domain. So because 0 is in the domain of 3 cosine 3x, we can just plug it in and end up with 3. So we get 3 times cosine of 0, which is 3 times 1, which is 3. Well, same thing about my other function. We have a limit of a constant number, and therefore we learned earlier that anytime we have a limit of a constant number, we get that constant number back. And therefore limit of 3 is 3. So notice that the underneath function has limit 3 as x goes to 0. The above function has limit 3 as x goes to 0. So that, therefore, I know algebraically that the limit of g of x also has to be 3. as x goes to 0. So as x goes to 0, since the upper limit and the above function and the below function both have limit 3, then g of x also has to have limit 3. By the way, that graph I showed earlier, I said, well, it turns out that that graph is actually the graph of this very thing. I have 3 cosine 3x. That's my red graph. Y equals 3. That's my green graph. And my purple graph was sine of 3x over x. So this is a really nice visual of the squeeze function. And it's, in particular, it's the squeeze function that we looked at. So you can see visually that the 3 cosine 3x, that's our red, is always underneath in the interval I cared about, in the interval from negative 0.5 to positive 0.5. The sine 3x over x was always in the middle on that interval. And then the y equals 3 was always on the top on that interval. Since the green and the red both converged at the point 0.03, squeeze theorem says the purple graph has to also converge at the point 0.03. So this was, in fact, the example that we did there of finding the squeeze theorem. I should say finding the limit using the squeeze theorem. So using that squeeze theorem, we found the limit of this g of x to be 3. Like I said earlier, these functions are sometimes hard to come up with, but once we have these functions, we can apply the squeeze theorem. We're not going to do the squeeze theorem a lot in this class because there are other methods as well beyond just the squeeze theorem. In fact, there are lots of other techniques that exist to find limits. We're going to look at some later ones, some different ones later on in this class. Not in this section, but later on, we will find some other techniques. There's also the case that people will memorize some special limits. For example, the limit of 1 plus x to the exponent 1 divided by x as x goes to 0 is actually equal to e. So sometimes there's some weird limits that pop up a lot in certain circumstances. This is one of them. So this is the limit for e. This is a good example of a special limit, one that certain people just know off the top of their heads. So I don't expect you to memorize a lot of special limits, but I just want to state that they are out there. And if you go on further into math courses, you will come across some of these limits that you just know. So that is it for this section.